Alrighty, good morning, everyone. Just before we get started here, let's just do a little accounting of where we're at. So, it's a little bit behind on the schedule, but that's all right. One of the last sections is fairly quick, so we can sort of catch up without too much trouble. I think the homework for today is 7.5. So we'll have some time later, I think, to talk about that. And then, so let's see, Thursday, Friday, Monday, Tuesday, Wednesday. Right. Okay, so I think today we're going to do 7.6. And then the this is the 23rd final. Yeah. Okay, so the final is here. And then I'm shifting back and forth here. So test 4, that was weird. Will be here. And then we'll do review for the final. And I'll try and give you a practice final in here somewhere. And then these are just going to be covering a few sections from chapter 8, parts of what are called sequences and series. So that'll be there. And then the homework, again, there is a schedule for the homework, but I think at this point we're getting kind of close. So as long as you kind of try and hit some markers, 7.6 would be great if that was tomorrow, and then we can start funneling in the rest of these homeworks. The last test, I think, only covers, it doesn't cover 8.7. That'll only be on the final, so there's that. I haven't graded the tests yet. That's part of today, so sorry that that's not back, but you'll have them either tonight or certainly by tomorrow morning. And lots of past homeworks are filtering in. I got like 19 different homework sets to grade, like singletons here and there, so I'm playing catch up myself, but it's a good idea to get it in. It's all graded on completion anyway, so again, that's good. 7.5 you just saw, but just sort of as a reminder, the basic idea is if you are in a constant force setup, so then the work formula is just super easy. You take the force and you multiply it by the distance, and that's it. How far do you move something that weighs a certain amount, a certain number of feet? And so then those will be written either in foot, pounds, or in Newton meters, which is joules. So great. If it's not a constant force, so if it's like a variable force, pulling up a rope, having the sand drip out, or you're lifting things of different sizes or something, then really just the work is equal to the integral of the force function. So it just comes down to that sort of pretty simple equation. You just have to figure out what the force is therefore going to be at a specific value of x, like the height above the ground, or that's typically what it is. Or we might have a spring where the special case is just, with the Hooke's law is that you get kx dx if you're talking about Hooke's law and springs. So in that case, it's even easier. You just need to find out what K is, and that'll be usually, you'll give in some characteristics of the spring, figure out the spring constant, and then it's just how far do you stretch it or compress it off of its natural length. So it comes down to just that nice little formula there. And you'll get the, if it was a constant force, then this integral, you just integrate it and then multiply by the distance, and that will be the same. So these are sort of technically the same thing. It's just that the integral is a much more general formula. 7.6 is also, you don't want to lose sight that the formula is fairly simple. This is on fluid forces. So how much force is a fluid? It could be water, of course. It could be, I guess, mercury, or anything that you take in something and you submerge. So if you submerge a say horizontal, it has to be horizontal for this to work. If it's not, we're going to have to use calculus. So if you submerge a horizontal plate under the water, then the fluid force, or just the force, I guess, here, which is going to be measured in pounds, is just the pressure times the area of whatever your horizontal plate is. So you've got some water level, and you've got some plate that you submerged that's a certain distance down, and you want to figure out how much fluid force is being imparted on that surface. Now, how do you get all of these units here? Well, how do you get pressure? Well, pressure is just the density of your fluid. So if it's more dense, obviously you're going to have more pressure against it, times the depth. So the density of whatever fluid you're submerging your thing in times how far down you are. And then you multiply by the area. So, whatever the area is, length times width, could be a circle, could be a triangle, could be a weird shape. So the units on this are going to be, this is feet times feet, so it's an area, so that's feet squared. The depth is also in feet, so that's just how far down you are. So you're going to get feet cubed right there. So in order to get back to pounds, that means this is pounds per cubic foot. So there's your units, pounds per cubic foot, how far down you are, and then times the cross-sectional area, or the area of your shape. And that's
I'm just curious. So why does it say submerge a horizontal plane with the pressure part? Why did you write that there exactly?
Well, if the pressure on the object depends on the depth, then if you have the plate, look at it from the side. If your plate is horizontally placed, then depth is always the same. Depth is always the same.
Okay.
The thing we're going to do next is what happens if you turn it and rotate it up vertically. Then it's going to be different, because if you have a plate that's submerged up and down, then there's going to be less fluid force on the top of the object than there is at the bottom, because it's deeper. That should sort of make sense. The nice thing about this, if you've ever been swimming, right, is it doesn't matter if you're swimming in a swimming pool or you're swimming in the ocean. If you go down 10 feet, it'll be the same fluid, it'll be the same pressure on your ears, whether you're in a pool or you're in the ocean. So I don't know if that is like, well, of course, no duh. But think about it. If you're in a pool, how much water is above you versus in the ocean? There's a huge amount of water above you. So thank God it doesn't depend on how much water is actually above you, because you're not like adding up all the water above you and that puts pressure on it. Because otherwise, in the ocean, you die. If it depended, there'd be like billions of gallons of water above you pushing down on you. And it just doesn't work that way, which is very good. It doesn't rely on how much water is above you. It's just how far down you are. I don't know if you've ever thought about that before, but now you might be like, oh yeah, that would be bad. You're in this, yeah. So anyway, so what I mean by that is let's just look. Basic example here is if I took a rectangle.
It doesn't matter. Sorry,
Go ahead.
saying it doesn't. What you're saying, it doesn't matter how much water in that instance will be above you. It just matters how deep you are within it.
Right. Yeah. And maybe that's not something you've ever thought about before, because if you've ever been scuba diving or something, and you go down 50 feet or something, it doesn't matter that there's like 50 feet of water above you. It just has to be in the direction you're at. Maybe now you're like, why doesn't all that water above me crush me? And it's just because you kind of have like forces in every direction sort of balancing each other out, and the only thing that really matters is the depth. So, for example, suppose you had a box that was...
Wait, I'm just curious, though, because, just in an instance, there are some pressures which people just can't go to, certain things just can't go to that being crushed. So,
but that's
in
not...
terms of the ocean.
That only matters because of the depth, not because of like the billions of gallons that are above you. Like if you had a
So,
little shaft that was like a manhole sized hole and it was filled with water down to 100 feet, and you went down to 100 feet and you equalized your pressure as you went down, and it's the same thing as if you were in the ocean and you went down 100 feet. You would experience the same amount, even though there's a lot more water in the ocean above you.
okay, so just be crushed from all sides, basically. Your body actually couldn't take the pressure at that point.
Yeah, I mean, everything sort of balances out so that you don't have to worry about that volume above you. It's just a depth.
Okay.
Yeah.
Okay, I understand.
Okay.
Yeah,
So,
like with scuba diving, you practice in a pool, then you go in the ocean.
Well, that's a different reason, probably, but yeah.
No, the ocean's the best teacher. Just throw the students in there.
Well, I mean, that's right. Yeah, you all learn that taking swimming class anyway, right? Okay, so let's take this like tank, and we'll just fill it with water, which has a density, and I think sometimes we use this symbol delta. It's the lowercase delta. You know, the uppercase delta is a triangle. This is the lowercase delta, and the density of water is every cubic foot of water weighs a little over 62 pounds. So if you filled it with water, how much pressure would there be? How much fluid force would there be on the bottom of that plate? So how much force is here? So we're assuming it looks like it's the same. It's also the same thing as it's not only, instead of submerging yourself in the water, it's suppose you have a tank and you pour the water on top of it. It all has to be just that depth. I don't have to worry about all that water around it. I keep saying that. I'm going to stop saying that. So how much, if this is, this is now horizontal, so looking at it from the side, this is like 4 and this is 15, or look at it from the other side of 3 by 15. So it's like how much force is there from the water on the bottom of whatever this, this rectangular type tank. And according to the formula, it's nice. It's all at depth 15. So the force is just equal to the density times the depth times the area. So that was the formula that I just had on the first page. So you take the density, which is 62.4 pounds per cubic foot. I take the depth, which is 15 square feet. The depth, 15 feet, and I should write the units on here. Pounds, so I'm writing these in the right order. So pounds per cubic foot, I'm 15 feet deep, and the cross-sectional area will be in feet squared, and that's just 12, because it's a 4x3 plate at the bottom. So 62.4 density, 15 feet down, 12-foot cross-sectional area. And so that is 11,232 pounds of force. Pretty nuts, like on the bottom of your swimming pool. It's not a very big swimming pool, but.
So with other fluids, would it be a different constant instead of 62.4?
That's right. That's right. Yeah. So I don't have a list of them. We already talked about fluids. You're like, well, let's do water. Okay, what else? Well, let's put mercury in there. You're like, well, that's super heavy and it's also dangerous.
Where'd you get
the fluids you might know, but that number changes. The other two don't. Just that one.
So is 62.4 some kind of a constant value for analyzing pressure, or what exactly is that supposed to be?
It's the density of water.
Okay.
Yeah.
If
you took a bucket, not a circular bucket, right? A bucket that was 1 foot by 1 foot by 1 foot, and you filled it with water, that would weigh 62.4 pounds.
Okay.
Yeah. If you filled it with mercury, I don't know if you guys have seen mercury too much anymore. They used to put it in thermometers. You put the thermometer in your mouth and the mercury would move, and then depending on your temperature, it would mark it off.
Yeah.
But mercury is like that, that it's like, it looks kind of almost like a solid. You look at it, you're like, that looks like a metal, right? And then it moves and you're like, whoa, that's crazy. So it's super dense. It's super dense. You could probably even do air, right? I mean, like how many pounds does a cubic foot of air weigh? And you're like, does it weigh anything? The answer is yeah, it weighs something, but it's certainly small.
1 atmosphere.
Right, there you go, right? So I don't know what the density of air is in terms of, cubic feet or pounds per cubic foot. We could look that up in a minute. We'll do that. So if it's the same constant density down, that's the formula you use. Just like for work, if you move something a constant force and you have a certain distance, you just multiply the numbers together. The problem is what's the fluid force on the side of the tank, on any of the sides of the tank? So that's, you have to,
Hi,
look back
sorry.
at the notes. You joined late. Watch the video. 7.5 and 7.6 were supposed to be due today. We didn't do 7.6 yet, so it's due next time. Join on time and you'll see that. Just stop interrupting for a little while. Let me talk just a little bit.
Sorry, I was just
let me talk. Shut up.
Okay.
Shut up. Sorry. Just be quiet for a minute. You can do it. So what about the side of the tank? So this is 15, and this is 4, and this is 3. So what is the fluid pressure on the side of the tank when you fill it with water? Either that, yeah, we'll do that one. So the deal is this: if you filled it with water, you probably would realize that the force on the bottom is greater. On the bottom, this little part right down here, and it's less up at the top. So the force is going to be less up here because it's not as deep. I mean, it's just a little bit of water versus, it's like you're just like 1 inch down versus 15 feet down. So the problem is it's not a constant force because it is a vertical plate. So what do you have to do? What you have to do is you have to Riemann sum it. You have to take that side. So this is 15, this is 4, and you have to chop it into little pieces like this and pretend that those are all horizontal and they're at the same depth down. And as you let as Riemann sum, you're going to take the limit as these things shrink down. So you can kind of pretend like you have infinitely many like horizontal ones. So on each one of those, you can do the force. And then you can add them up, and then you'll get an approximation, and then you take a limit, and you'll get your answer. So on one of these little strips here, how much force is there on one little strip in the middle? Well, because you're pretending that it's like practically horizontal, it's got a little bit of depth, so that's not quite right, but this is an approximation. Then the force on that little strip is going to be basically constant. It will be 62.4 because that's the density. We're going to put in the depth here in a second. What is the cross-sectional area? This is the only hard part really in these problems is usually how do you do the depth and sometimes the cross-sectional area. In this case, what is the cross-sectional area of that little strip? Well, that's expanded out, but it's 4 units wide because it's 4 units wide. The width of this here, or height, or however you want to say it now that it's oriented, is now my delta y. Because this is now where my Riemann sums are coming out, cutting it sideways like this, so it's delta y. So my cross-sectional area is what? 4 times delta y, because it's length times width. Now the depth is going to be kind of the tricky thing because it depends on where I put my axis system. You can work this out in multiple ways, and this will depend on the location of the x-axis in your picture. So we can work this out in a couple different ways. Sometimes you want to put your x-axis right at the top of the water, and sometimes you're going to want to put it at the bottom of the water, and you're just going to get slightly different answers or slightly different setups. You'll get the same answer because they all represent the force. It's just the context on what we're doing. So suppose we're going to do a couple examples like this, but suppose we put the x-axis at the top of the water. Can you separate those cats? Sure. Okay, so if you put it at the top of the water, then this top of the tank will occur at y equals 0. What is the bottom of the tank occurring at? That'll be at negative y equals negative 15. So the bottom of the tank is at y equals negative 15, and the top is at 0. If y is 0, then what is the depth? Well, if y is 0, then the depth is 0. That makes sense. The one that's a little sneaky is if you're down here 15 units below, then y on this axis setup is at negative 15. The depth is 15. So you can see in this case that the depth is just whatever the opposite sign is of y. If I was 7 units down, my y would be negative 7, and my depth would be 7. So all I do is I just take the negative of whatever the y coordinate is, and that will give me my depth. So that's the force on that one little strip. So if I just put equals here, I get 4 times this, and I have a negative. So negative 249.6 times y times delta y. And that's the force on the strip. So what's the approximate total force? This is a Riemann sum. So the approximate total force is I'll just add up all of these minus 249.6. And really, if I do this the way I did it before, these are like different y's. So y, the little I subscript goes on there. And that's that hopefully should make sense as the Riemann sum. It's just density times depth times cross-sectional area, because that's the formula for force. Now, and then I add them up. If I wanted to get the exact force, then I have to take the limit as I get more and more and more and more strips, which we think it's like n goes to infinity. Or you can think of it as delta y is getting to 0. So all these little strips are getting thinner and thinner and thinner. And here's the equation I end up getting. It's the integral of minus 249.6y. So the yi becomes y. The delta y, just like every time we've done this, becomes dy. And then the bounds are, well, from the bottom of the strip, or from the bottom of the side to the top of the side, it's going to go from y equals negative 15 up to y equals 0. And so you can just integrate that, and you can plug in the bounds, and you can get y squared over 2, plug in 0 and 15, make sure you plug it in correctly so that the negatives all work out. And if you do that correctly, I think you get 28,080, and this is measured in pounds of force on the side. So that's the setup. If you set up your axis system, cut it into strips, use the basic formula, density times depth times area, add them up and take a limit, and you get down to this kind of equation down here. So what I'm going to do is I'm going to do that two other ways, and then we'll give like sort of the basic general formula for this so that we can apply it to other things. So just give me that, and then we can have questions. So that's one. The second way is we put the axis system, put x-axis at the bottom. And you're like, well, why would I put it at the top or the bottom? You'll see as you go through that sometimes the equations, part of the equation is easy in one way and the other's hard. And if you move the axis, the other part's easy and the first part's hard. So kind of not easy to put it somewhere where they're both easy. One of them's going to be tricky and the other one is going to be easier. So you'll see as we work through the example. So let's try this again, where we have our axis system, where now we're going to put the x-axis down here at the bottom. So now the tank is going to go not from negative 15 up to 0, it's going to go from 0 up to 15. And when I put my little strip in here, then the distance up to the strip is the y coordinate, and therefore the distance is just exactly whatever y is. So, or the depth is whatever, well, let's see, no, that's not right anymore, is it? What's the depth? If y is 15, so if y now is up here at 15, what's the depth of the water? Well, the depth is going to be 0, because that is the top of the tank. That's the top of the tank. There's no depth at all. If y is 0, then that means you're sitting down here at the bottom of the tank, and the depth is then 15. But now this is where the tricky part is. You got to figure out what the equation is that relates these things. You know, if you're 7 units up from the bottom, then you're 8 units from the top. So if you can figure that out, the point is the depth equation now is 15 minus whatever y is. So instead of the negative of y, when I put the axis system at the top, if you wanted to figure out what the depth is, you have to subtract the y coordinate off of 15. So if I'm 1 unit up from the bottom, I'm 14 units down on my depth. So now what does my force equation end up being? Well, it's going to be the integral. Now the strips are going from 0 to 15. And just like before, I still have density times depth times cross-sectional area. And the nice thing is the cross-sectional area didn't change. It's always 4 across times whatever the delta y is. So that A part right there ends up being like 4, and this was delta y, and now when you take the limit it becomes dy. So like the area is captured there. The density is 62.4, and the depth is now 15 minus y. So it looks a little different. Let me just sort of recopy what we had before. Versus negative 15 to 0, it's 62.4 times minus y times 4 dy was the one we had before. I combined the 4 and the 62, but it's density, depth, cross-sectional area. And both of those, when you work them both out, they both end up being this 28,080 pounds of force on the side of, on that one side of the object. So those are the two integrals. Now, here's the final thing, and then see if you guys have any questions. If you think about this as the center of mass, it's a nice little shortcut. So if you took the entire plate, so it's 4 wide, 15 here, and you condensed it all down into the very center of this object. So we haven't really talked about what center of mass is, but maybe not too surprising. The center of a rectangle is in the center. So it's 2 units over, and it's 7.5 down. So half of 4 and half of 15. So that's the deal. If you condense the entire side, pretend like it's all there, but now you can like take the whole plate and actually flip it so that it is horizontal. But you just have to put it at the center of mass depth. And the point is now the force is going to certainly turn it like horizontal. Then the force is just straight back to, I don't even need to use integrals anymore. It's just density times depth times the cross-sectional area. So this is going to be 62.4 times 7.5 is now the depth of my center of mass. And what is the area? Well, the area is still length times width, and that's 60. So pounds per cubic foot, feet, and feet squared. And this also ends up being 28. So if you know how to do center of mass calculations on this, these turn out to be pretty quick. Of course, the problem is I'm going to take an object that looks like this and like, well, crap, I don't know where the center of mass is anymore. So you have to use an integral. Okay, just wanted to get that out of the way. And now, are there questions on any of those parts?
So I got something kind of similar, except I use the first integral instead of the second one below it. Would that still be valid or no?
I mean, all the setups are exactly representing the same thing, which is the force of the side on the object. It's just calculated in 3 different ways.
Okay. I just want to clarify that. Thank you.
Mm-hmm. Okay, so let's think we can do one more here, and then, well, I don't know. So that means if you try to do, say, a circle, you know, what happens if you took, for example, and you had a circle radius 2. and it's submerged under the water so that is 5 feet. Turning it off for a second. So the question is how much is the force, the fluid force, on this object? Suppose it's water. If it's not water, then they'll just say, here's the density of whatever this thing is. We'll look up what it is. One of the examples in the book, they might say, use concrete, which is like the liquid version before it solidifies, or even not, maybe really won't even matter, but which is like 150 pounds per cubic foot. And it's multiple times. We'll look up mercury in a second. So suppose you have something that's a plate that is submerged this way. So it's like, I don't know, like you go to the aquarium and you want to look under the water and they make like a little 2-foot portal made out of glass or something. You can watch all the fish, you can watch the sharks or whatever. How much, how much do you have to reinforce that? Because how much force is being imparted on that? Well, the hard way, you're going to do this a couple ways, and we'll do it the easy way for starters. You can't always do this, but if you use the center of mass idea, then you can pretend like everything is concentrated right at the center of the circle, and instead of the plate being this way, you can then rotate it to the side. So how is that going to work? You'll have the force, again, is the density times the depth times the area. So in this particular problem, you'd have the density, again, 62.4. The depth of the center of mass, the way I've drawn it, it's 5 feet to the top and 2 feet then to the center. So this would be 7 feet down to the center. And then you multiply by the area. And what is the area of this? Well, it's a circle. So that's just a circle. So it's just pi times the radius squared. And so you can work all that out, whatever works out to be 62.4 times 7 times 4 pi, so 62.4 times 28 pi. I don't know, I don't have a calculator, but you can calculate it out. And that's it. I mean, and it's measured in pounds, because again, pounds per cubic foot times feet times square feet across the board. Before we get into the calculusy part on this, just take a quick break and get a drink or something, and then we'll be back in like 5 minutes. So we're a little bit early break, but that's okay. So we'll see you